But the biggest threat from solar storms isn't to our technology. Radiation can kill. NASA's Neil Zapp is all too aware of the dangers faced by astronauts on all space missions.
Our major problem is that we don't have control over the situation. It's not as easy as turning something off or sending someone home or taking them out of an area. It's very difficult for us to get people out of harm's way once they're in orbit.
No one knows when the next solar storm will strike. And they travel so fast, early warning is next to impossible.
Confirm ignition and the thrusters go.
In 1972, NASA has a close call. In April, Apollo 16 lands on the moon. 8 months later, Apollo 17 touches down.
During the space between these two missions, between Apollo 16 and Apollo 17, there was this large event.
A storm breaks on the surface of the sun. 10 billion tons of radiation rains down on the moon. Unlike the Earth, the moon has no atmosphere to protect humans from the effects of radiation. If the astronauts had been here when the storm struck, they would have absorbed a potentially lethal dose of radiation.
It wasn't by planning, it wasn't intelligent planning that provided for putting the event in the dead space. It was actually a little bit of luck of the draw at that time.
But what happens when a massive solar storm is aimed straight at the Earth? We can't simply move out of the way. For all their power, these bursts of radiation are mere ripples spreading into interplanetary space. The solar storm that hit Quebec is a tsunami. March 13th, 1989. Across the Northern Hemisphere, millions witness a dazzling light show called the Aurora Borealis, the Northern Lights. These sparks are a visible sign of a clash hundreds of miles above the Earth's surface, a war between the sun and the Earth's invisible defense shield, the magnetosphere. Nicola Fox knows the shield like her own backyard.
The sun gives us everything that we need to be able to survive here on Earth, but equally it could take that all away in a split second if we didn't have the magnetosphere to protect us.
The magnetosphere completely envelops the entire planet. This invisible shield flows out from the Earth's core. It punches through the South Pole, cocoons the entire Earth, then plunges back down through the North Pole. Without the magnetosphere, all life on Earth would be vulnerable to high-energy solar radiation. These particles can penetrate living tissue and cause severe damage to cells. When the March 13th radiation cloud collides with the shield, most of the charged particles are deflected safely around the Earth and back out into space. But some radiation does leak in at the poles.
And that really churns up the whole magnetosphere, makes it go to very different configurations than it would normally be in. And in order to redress that balance, because nature always has to be balanced, the aurora are powered.
These mysterious displays of colored lights form when solar particles slam into gases in the atmosphere and cause them to glow. The more powerful the storm, the more dramatic the auroras. This high-altitude battle can cause problems for airliners. At the poles, the atmosphere is especially vulnerable to large bursts of radiation. The wave of energy causes havoc in the upper atmosphere, disrupting GPS systems and blacking out radio signals.
During intense storms, passenger aircraft have to divert to lower altitudes in order to regain communication with air traffic control.
On March 9, 1989, as the radiation from the flare arrives at Earth's upper atmosphere, the battle with the magnetosphere begins. But in Quebec, the power stays on. 4 days later, on March 13th, a second wave of radiation hits the Earth's atmosphere, and the aurora puts on an awesome show. As the northern lights dance in the sky, the lights in Quebec suddenly go out. How does a radiation cloud high in the atmosphere shut down an electricity network on Earth? To find out, NASA develops the OSO-7 satellite. It can aim a battery of UV and X-ray telescopes at the sun. The mission will give scientists their first glimpse of a monster. This white spot might not look impressive, but it's the first image ever captured of the most powerful event in our solar system. It's called a coronal mass ejection, or CME. 10 billion tons of material explodes from the atmosphere of the sun, an enormous eruption. Without Earth's magnetosphere for protection, high-energy particles from the blast could begin to strip away our atmosphere. If a solar flare is the muzzle burst from a gun, then the CME is the bullet. Scientists still don't know exactly why CMEs occur. They're formed from the sun's corona, the atmosphere that surrounds the sun and stretches millions of miles out into space. Temperatures here reach nearly 3 million degrees Fahrenheit, almost 200 times hotter than the surface.
There are magnetic turbulence and magnetic forces lower down in the solar atmosphere that cause literally the outer atmosphere to be blown out into space.
CMEs are an electrified tangle of charged particles and magnetic fields, a superheated bullet of matter from the sun. A CME looks like a solar flare, but it's 100 times more powerful.
Before we knew of CMEs, we thought that the magnetic storms that occurred on Earth were a consequence of this brightening that was seen at the sun, the flare. And as we've learned more about the sun, we've realized that it's the CME that actually causes the magnetic storm.
Roughly half the time a solar flare occurs, a CME follows. But it travels hundreds of times slower.
It is a mass of coronal material that's coming off the sun, and that travels with the solar wind that streams continuously away from the sun at about 1 million miles an hour. So it takes about 93 hours for it to get to Earth.
On March 9th, a solar flare kicks up a wave of radiation from the sun. The wave travels at the speed of light across space. It hits the Earth's atmosphere in just 8 minutes. The coronal mass ejection arrives 4 days later. This is what causes the blackout. Unlike a solar flare, a CME isn't a spray of radiation. It's a barrage.
And all of a sudden, this big addition of 1,000, 100,000 times as much energy is thrown at the Earth.
The CME creates immense electrical currents in the ionosphere. The upper atmosphere practically crackles with energy. The auroras light up the sky as far south as Texas. Rivers of charged particles flow through the atmosphere and induce powerful electrical fields 60 miles below at the Earth's surface. Suddenly, with no warning, a vast current jumps onto the power grid. The surge races through the system, and the network overloads. the lights go out in Quebec.
We're talking about thousands of components in a power grid that are affected simultaneously, and there really is no place to run and hide from the effects.
The Quebec event was rare, but not unique. So how at risk are we? And when will the next solar storm strike?
For solar storms, it's always a question of when the next one will happen. It's not a question of will they suddenly go away.
To gauge the future threat, scientists need to know how often the Earth has been hit in the past. The hottest storms in the solar system have left their mark in one of the coldest places on Earth, the Arctic Circle. Locked within layers of ice is a history of the Earth. The ice keeps a record of solar storms dating back thousands of years. To see how often the storms hit, researchers look for a chemical they leave behind: nitrate.
You can actually core the ice and measure the nitrate abundances, and you find that the spikes in the abundances match up very nicely with some of the more recent intense storms.
By scanning ice cores, scientists travel back to an age when a massive solar storm struck Earth. A huge peak in nitrate reveals a solar storm that makes the Quebec event look like a firecracker.
The most intense abundance change that we see in the ice core data occurred in September 1859. It was so intense that we call it a superstorm event. It knocked out telegraph service in North America and most of Europe, and it was also seen all the way down in Calcutta, India at the time. It was a major worldwide event seen just about everywhere.
The 1859 storm is the most powerful solar eruption to hit Earth in 500 years. It's 3 times stronger than the storm that blacked out Quebec. If it had hit today, it would probably be catastrophic.
When you think of all of the services that rely on electric power, it's rather staggering to imagine the kind of a geographic footprint that one of these storms would have.
After a superstorm, the lights don't come back on the next day.
Most of the transformers that are used by the big power grids are custom order and can take months to replace.
Imagine months without power. Transportation grinds to a halt. The economy nosedives. No running water. No sanitation. Scarce food. Rampant disease. From the space age to the Stone Age, in the blink of an eye.
A solar storm would affect the power grid in an entire continent because these kinds of storms span the entire planet. It's unlikely that in your lifetime or mine we're going to see one of these superstorm events. After all, the ice core data was 500 years long, and there was only one of these events in 1859. But there are plenty of events that were a half as strong or even a third as strong. They are more numerous, and because of that, the long-haul effect of these things could be actually substantially worse than one major storm all at once.
It could be worse. The sun isn't the only star that produces solar storms. Astronomers peer far into the depths of space and watch stars being born and others die. A chance discovery shows just how dangerous space can be. Astrophysicist Eric Feigelson is researching deep space, looking for streams of X-rays. But what he stumbles upon blows his mind.
Instead of finding what we thought we would find, we instead found these rapidly changing X-ray sources associated with young stars. And we were quite puzzled, frankly, for some years.